So today, our group will present a discussion on future concrete materials, a topic that reflects not only environmental responsibility but also engineering innovation. Cement production alone contributes around 8% of global carbon dioxide emissions. Therefore, our duty as future civil engineers is not limited to building structures. It is about building a sustainable future. Our goal in this video is to inform, defend, and debate why emerging concrete technologies should be adopted in the construction industry. I would like to begin by presenting carbon cure concrete, a solution that reduces carbon emissions while preserving the traditional concrete process. Carbon cure technology involves injecting captured carbon dioxide into freshly mixed concrete. The carbon dioxide chemically reacts with calcium ions, forming calcium carbonate, which enhances the compressive strength and durability of the concrete. More importantly, the carbon becomes permanently embedded in the mix. This system is already implemented in over 300 concrete plants around the world. It does not require major changes in current batching systems, and it's making it ideal for rapid adoption. From a resource standpoint, this technology integrates captured industrial carbon dioxide for materials, injector and batching technologies for equipment, civil and environmental engineers for people, publish engineering papers from ACI and NRMCA for information, and industry's feedback from companies like Lafarge and Holcim for engineering communities. In terms of innovation, carbon cure transforms waste into structural value. It is a clear example of a circular engineering. To those who argue that this technology only reduces emissions moderately, I respond by highlighting its practicality and low cost. It offers immediate impact without disrupting workflow, making it the most implementable future material today. That's all from me. Thank you.
While I respect my teammates' position, I propose a more fundamental change to how we build. My argument supports the use of geopolymer concrete, a material that does not rely on cement at all. Instead, it uses waste materials such as fly ash or ground granulated blast furnace slag, combined with alkaline activators to form a stable and durable binder. This results in concrete with significantly lower carbon footprint, up to 80% less than ordinary Portland cement. It is also more resistant to chemicals, fire and extreme conditions, which make it suitable for use in coastal structures, sewage plants, and industrial floors. From a resource integration point of view, geopolymer concrete utilizes industrial waste, control chemical mixing systems, chemical and structural engineers, global research databases such as Elsevier and Science Direct, and validation from international construction communities. The innovation in geopolymer concrete lies in the complete replacement of hydration chemistry with aluminosilicate polymerization. This is not a minor upgrade, it is a transformation of the entire concrete production philosophy. Some industry players argue that geopolymer concrete is more expensive and harder to control. However, I counter that with life cycle analysis. The reduced maintenance costs and extended lifespan make it economically viable in Malaysia, where we have abundant waste materials like palm oil, fuel ash. Geopolymer concrete offers not only sustainability but also a strategic use of local resources. As engineers, we must ask, are we solving the root problem or are we applying temporary fixes? I believe geopolymer concrete is the solution that targets the root. Thank you.
Both previous speakers have highlighted material focus on sustainability. I take this debate further by emphasizing the need for intelligent and adaptive material. My argument supports self-healing concrete, a material designed to autonomously repair its own crack using bacteria and chemical capsule embedded during the mixing process. When crack form, and moisture enters. This agent become active, producing calcium carbonate to seal the crack. This technology not only extend the life of concrete structure but also reduce cost and frequency of maintenance, especially in difficult to access areas such as tunnel and bridges. From the resource perspective, engineering activity 1, this material involve microbiologists and civil engineer people, bacteria, spores or healing agents, material, encapsulation, and mixing technology equipment. Advice, research from the Delft University and IEEE journal information, and real-world input from the infrastructure contractor. The innovation engineering activity 3 is not in material composition alone, but in function. Self-healing concrete react to damage in real time, representing the new generation of intelligent construction material. Stakeholder we interview raise valid concern engineering activity 4, including the high initial cost, regulatory uncertainty regarding biology agent, and concern about the long-term performance in tropical climates. However, our proposed mitigation are clear: government pilot program incorporation into CIDB standard, and specialized training for engineers. So, I conclude that while Jolly Polymer and Carbon Cure address sustainability, self-healing concrete offer long-term resilience. It may be the most complex, but it also the most forward-looking.
Thank you to my teammate for presenting their argument. Now I will conclude this debate by comparing the three technologies and summarizing our position. Carbon Cure concrete is cost-effective, easy to adapt, and moderately reduce carbon emission. It is an excellent short-term solution for ready-made and government building. Meanwhile, geopolymer concrete offer the highest sustainability performance, turning waste into durable structure and eliminating cement entirely. It is the best suited for infrastructure with chemical or thermal exposure. Meanwhile, self-healing concrete is the most innovative and durable, ideal for long-term projects such as bridge, marine structure, and nuclear facilities. All three materials demonstrate complex use of engineering resources, bring forward critical innovation, engineering activity 3, and present real consequences to society and the environment, engineering activity 4. We gather feedback from stakeholders in construction, engineering, education, and policy sector. Most welcome innovation, but all emphasizes the need for pilot project, industry guideline, and cost management strategies. Based on this, our group recommend a entire national strategy. Use carbon cure in public housing to start immediate emission reduction. Use geopolymer concrete in industrial and coastal project. And deploy self-healing concrete in strategic high-rise structure. In conclusion, future concrete materials are not distant innovation. They are available, tested, and necessary. As civil engineer of the next generation, we must not only build strong but build smart. Let us be the engineer who solve today problem without compromising tomorrow solutions. Thank you.